So it's a pleasure to have Ola Svensson talking at our conference. He is a professor at EPFL in Lausanne, and he will be talking about learning-augmented online algorithms and the Primal-Dual method. Thanks for talking online, Ola, and yeah, hope to see you physically in Moscow in some near future, you know. Yeah.
Definitely. So, thanks a lot for inviting me. So please feel free to interrupt me at any time. I don't know, maybe I will ask some questions, see if you answer. So this joint work with two students of mine at the Bamas and Andreas Maggiori. So I wanted to, start to talk, you know, the outline is that I would like to start to introduce this, what is the learning augmented online algorithms. Then we will introduce this very powerful Primal-Dual method by doing a case study with one of our favorite problems, which is the set cover problem. And by doing so, by studying Primal-Dual method for the set cover problem, we will see there's a very natural way of incorporating predictions. We call this Primal-Dual learning augmented, and we'll see then how to instantiate this in a fairly systematic manner also for other problems. All right, so let me start with defining what is this learning augmented online algorithms, and you know, maybe we should start with online algorithms. And here I like to take an example. Suppose you go to Google, you search best graduate school, then maybe you go to Yandex and you press best grad school, and then you wait, right? And then you get some responses. You see here the responses makes perfect sense, but then there's this weird thing in the beginning, which is of course an ad then allocated by an online matching algorithm.
It looks like it's biased on your search history, this thing.
Yeah, or maybe this is not exactly what was searched. I don't know. It could also be. So right. So you know, now we have you know a little bit more serious. We have advertisers, we have searches coming online. Maybe someone says I'm thirsty, so some ads are more relevant than others. And without knowing about the future searches, we have to make up our mind which ad to display. So this is a matching question. Okay, so maybe you assign the Pepsi ad to this search, and then a new search comes. Now we have Pepsi run out of budget, so we assign the Rivella, and so on. Okay, so this is what we call an online question, because the searches, in this case, the searches arrive online and we have to make immediate, irrevocable decisions without knowing about the future. So the way we evaluate, traditionally, the way we evaluate online algorithms is through its competitive ratio, which says that, you know, an algorithm it's very related to approximation algorithms. In approximation algorithms, we have a trade-off between time and solution quality. Here, we kind of have a trade-off between solution quality and knowledge about the future. So an algorithm is C competitive if for any input sequence, it finds a solution with cost at most C times opt if we minimize. So here, opt is the best solution if you would have known everything in advance. Okay, so we are competing with the best solution when we have full information about the instance. And if we maximize, we would like to find something of value at least C times opt. We will mainly focus on minimization questions, so that's important. Okay, so I don't know how familiar with the online algorithms, but you know, a classic example that fits Switzerland very well is a problem called ski rental, where you know the question is the following. So at the beginning of each day, you have to decide whether you want to buy skis at a cost of B or rent skis for that day at the cost of 1. Okay. The issue is that you do not know how many days you will be skiing. Okay. So now you have to make up your mind, you know, should you buy skis or rent skis? So do you know the optimal strategy here?
Well, I would just buy skis.
You would also buy, but suppose you buy the skis. If you buy the skis the first day, right, you pay B and then you injure yourself. So the optimal strategy would have been to just rent skis for 1 day and you pay 1, but you pay B. So your competitive ratio would be like B, which could be arbitrarily bad. So it's not a good idea to just buy skis the first day. Suppose you don't like skiing. So any other ideas?
Well, yeah, then it's for me it's difficult. I'm not impartial.
So
should you flip a coin at random at every day with a certain probability?
yeah, so it turns out, in fact, that if you allow yourself to use randomness, you can do better than deterministic. So the best deterministic competitive ratio for ski rental is a factor 2. And let me explain that. The randomized is a little bit more complicated, but 2, how do I do 2? So I wait rent for B minus 1 days, then buy. Okay, then buy. All right. So my deterministic strategy is that I will rent for B minus 1 days and then I will buy. And this is kind of robust because suppose the true number of days I would like to ski is less than B, then this is in fact optimal. The best thing you could do if you ski less than B days is just to rent. Now, if you ski more than B days, you should have bought at day 1, right? Like Andre, then you should have bought. So then opt only pays B, and I will pay 2B minus 1. I will pay B minus 1 for renting the first B minus 1 days and then buy. Okay, but that's the worst case for me, so I will always be too competitive. And it's not hard to see that this is the best you can do for deterministic algorithms. If you allow for randomized strategies, you can see here that, in some sense, if you allow for randomness, this is not the optimal algorithm because I was a 1 competitive for those instances where you ski less than B days in this deterministic algorithm. And if you randomization, you can balance things out. And it turns out that if you use randomization, the right ratio is this one, E over E minus 1. Okay, so that's the kind of the classic 2 competitive algorithm ski rental. We will return to this algorithm to this problem later in the presentation. Okay, so that's the traditional way of evaluating the online algorithms. And if we return to like the add allocation or the matching problem, then the basic greedy algorithm is in fact the best algorithm you can do in deterministic. And this gives you a half competitive. That's the best you can do. And if you use randomization, then a classic paper by Vatsani gives you 1 minus 1 over E. And this is, again, the best. So this is a completely understood question when you have a matching problem where vertices arrive on one side of the graph, on that graph. But, maybe this is a little bit pessimistic guarantees. And, you could imagine that if you want to assign ads, you have some knowledge about what kind of searches could appear in the future. And, they are pessimistic in the sense that they work for any possible input sequence. Okay. So last problem is about choosy bride.
It's known also as the secretary problem, I think, in the West.
Oh, the secretary problem. So it's a little bit different in flavor. There, it's crucial that the candidates arrive in a random order, for example. So then you sample and select. Here, they're not exactly the same, let's say, but they're both. It's true that they're related. That they're both classic online questions. Okay. So let's make the point that if you actually expect to assign ads, then maybe for any input sequence is a little bit pessimistic. So look here. So to prepare the presentation, I made this search in the UK. No, yeah, I looked at the Google stats in searches made in the UK for the term Premier League, which is their soccer league. And you can see, the searches of Premier League are pretty systematic. Okay, so this is the peak when a lot of searches have been made for Premier League. And you may guess that this is, the weekend, the Sunday when there is games of Premier League. Okay. So this would imagine that, okay, so maybe we can use statistics of searches to improve our algorithm. And that brings us to like ML algorithms that I don't know much about, but you can imagine an algorithm that does very well when the data is as expected, but unfortunately these arguments seldom come with guarantees, so it may even output something that doesn't make sense. Okay. And again, to make that point that sometimes it's hard to predict the future, let me expand this with one more week. And you see that there's something weird going on. And this is not a made up example, this is a real example. So there's 1 week when the British do not search Premier League. So this is Sundays again, but then there's like they skipped 1 week for some reason. Any ideas why they didn't search for Premier League during one Sunday?
Some national holiday.
Yeah, you can imagine like some maybe some scandal with the royalties or something. No, I was kidding. It was not that, but it could have been maybe. But no. So this is like, you know, this is when they're World Cup qualifiers. So there were like no games in Premier League this weekend. So that's. I guess there is a rational explanation, but it's not immediate. Okay. So this motivates, you know, that we want to somehow get the best of both worlds. So what I want to make is like online algorithms, they have really robust, I mean, by definition, they're guaranteed the competitive ratio is with respect to the worst case. But maybe they don't work so well on typical instances. And ML have no worst case guarantees, but work well in typical instances. And somehow learning-augmented algorithms, online algorithms want to get kind of the best of the both worlds, okay? So the way you should think about this is that we have an online algorithm that has access to predictions about the future. So in the ski rental, for example, you have access to a predictor that tells you the number of days you would like to ski. But since we do not have any understanding of how these algorithms really obtain their prediction, we want to make no assumptions, okay? So in particular, we don't want to say that the predictor is correct, because if the predictor is correct, right, there's nothing to do. If you know the number of days you're going to ski, okay, then it's an easy question. So what kind of guarantees can we hope to get in these models? We have an online algorithm that has access to the prediction of the future, but we don't make any assumptions regarding the quality of the prediction. So basically, it's the study how can we make decisions using unreliable predictions. So what kind of Desiderata, how would you evaluate an algorithm, right? So there's 3 kind of things that one can think of at least. What would you say? So what would we like if the predictions are correct? So if
some kind of competitive ratio with respect to machine learning algorithms or
right. So
algorithms.
well, we call it, yeah. So exactly. So we would like to say consistently, if the predictions are correct, then we want our algorithm to do really well, right? So if you have predicted the right number of days you're going to ski, well, you should do close to optimal, you know, you should not be much worse off. But then at the same time, we want to have robustness, saying that, hey, if the prediction is terrible, even adversarial, we want to maintain our robust guarantees, or the worst case guarantees, okay? So even under the adversarial predictions, we would like that the algorithm maintains a worst case guarantee that's ideally not much worse than the best known online algorithm. So basically, we want an algorithm that if the predictions are great, we want to do great. If the predictions are terrible, even adversarial, we want to bound the damage, okay? And now, a natural third thing that I will not talk about in this talk is like you want also to have smoothness. You know, maybe it's too much to hope for that the predictor is perfect. So you want like the consistency to be smoothly degrading in some way of defining how accurate the prediction is. So in the ski rental example, right, if the predictor is off by 1 day, your algorithm should still give a very good solution. So, but I will focus on consistency and robustness in this talk. Okay, so yes, so as an example, let's return to ski rental. So here's the same problem, but now you also get, you know, as input a prediction P of the number of days that you're going to ski. So now what can you do? Well, if you just want to have robustness, it's easy. You can just, do not listen to the predict at all and just run our online algorithm, okay? But that's kind of bad consistency because we didn't use the prediction at all. So we are still just a too competitive algorithm. But what if we just listen to the predictor? So suppose the predictor says that you're going to ski 10 B days. So suppose P is equal to 10 B. Then if you greedily listen to the predictor, what do? Then you just buy, right? But then the true answer may be that you should just ski 1 day. Because the predictor could be arbitrarily bad. And then you're 10 B competitive, okay? You're B competitive, which is kind of very bad, okay? So if you completely trust the predictor, you have excellent consistency, but you have terrible robustness, okay? So it turns out that for many questions, and most interesting questions, you need to put, there's a kind of a parameter, how much you should trust the predictor. And that kind of calibrates then the trade-off between consistency or robustness, okay? So it turns out that for ski rental, if we set this parameter lambda 0, lambda equal to 0 basically means completely trust the predictor, and lambda equal to 1, just run the online algorithm. And here it turns out that if the prediction is that we should buy, then if we wait lambda B days, it's similar to when we waited B days, then we get a too competitive algorithm, right? In the previous. So if you waited for B days before buying, or B minus 1 day, you got too competitive. If you wait for lambda B days, then you become 1 over lambda competitive in the worst case.
Well, there is a small question in the chat, I think. Do you predict at day 1?
Yeah, sorry. So yes, at the moment we assume that you get the prediction at day 1. We get one prediction. In other problems, you can imagine to, for example, in scheduling, that you get predictions as the instance. Here, there is only one variable to predict, and we get it at day 1. Yes. But in fact, here you see that if you want to have some robustness guarantee, you will wait lambda B days in any case to buy, no matter what the predictor says. So it would be fine enough to just get the prediction before you would actually buy. Did that answer your questions, Vanaya? Maybe. Does it make sense to update the policy after a few days? So here, I mean, here I don't know if it makes sense because we have kind of all the information to start with, right? So you could think of so where it makes sense, for example, again in scheduling, right? You could actually observe the predicted jobs and what happened in reality. So based on your history, you could actually see how good your predictor has performed so far. And then it may make sense to, change how much you trust your predictions for the future. But here I'm not 100 if it makes sense to update your policy.
Yeah, in some sense, you can imagine a predictor giving you a number every day, but then like a different number.
If you do perfect. If you look at the repeated ski rental question, then I completely agree. Like, then it makes sense. Hey, the predictor was terrible at instance 1, so let's not listen to him at instance 2. But if he did great so far, you may want to increase your confidence. It's a little bit like the expert question. Any more questions?
Also, another question in this from me. In this model, we don't really care what exactly does the predictor say, in a sense that if he would say, I don't know, B plus 1 or 10B or million B, it would be just the same, right?
Yeah, in this algorithm.
Yeah, in this
algorithm. You're right.
Yeah.
Yes, you're right. I will come back to the ski rental later on. Okay. It turns out that that for ski rental, I think that is actually you get an optimal trade-off by only looking. Okay, so this is not so. Actually, this is merging quickly growing line of work. So in fact, it was introduced on a Learning-Augmented in ICML 2018 by Lukurz and Vasilevsky, and now become very, very popular. Basically, you can revisit all the questions you devised online algorithms for. But then it was actually a very similar model was studied already in 2007, I noticed, in EC by Madjan, Nasrazadeh, and Saberi. So there's all this excitement, and you can adapt what you have done in streaming or online algorithms by using predictions. So the way we entered this then was that we were reading up about, or my student was reading up about the Primal-Dual method for online algorithms, and that's what I'm going to explain now. And then there's a kind of natural way of adapting this framework using predictions that allows us to unify some of the previous results and obtain some new ones. Okay, so now I would like to explain this method, which is a very nice method. This is also a very nice monograph by Nip Buchbinder and Josef Sefinauer. Okay, so we will look at the set cover problem. So what is this question? So I have sets S1 and S2. I know these sets in advance, but I do not know which elements will arrive in the future. Okay, so it's an online question. I know my sets, but I don't know the elements that will arrive. So now when an element comes, we need to cover it. I don't need to cover it by picking a set. I just need to fractionally pick sets so that I cover each element by one unit. So here, let me give an example. So when this element comes, the yellow one, it can be covered by both sets, right? Both by S1 and S2. So now what I need to do is to increase the fractional variables corresponding to these sets so that this element is covered. So I need to put the constraint x1 plus xs2 to be at least 1. So I have each set can be picked in standard set cover that you may know, you need to pick each set integrally. This is the fractional version where I can pick sets fractionally. And my goal is at the end of the game to minimize the total number of sets I picked, or fractionally the total number of sets I picked. Okay, so here I got this. I need to satisfy that. Well, maybe you put that I cover S1 with fraction 1/2 and S2 with fraction 1/2. That would, for example, satisfy this inequality. And now one other element comes, this one here, and it can only be covered by S2. Now I'm not allowed to decrease variables, so the only thing I can do is to increase S2 to 1. Okay, so my solution here has value 1 plus 1/2, 1.5, whereas the optimal solution would have been to only take S2, which has value 1. But you know, I solved it online, so I could not have known in advance which elements to arrive. Okay, so that's the fractional set cover question. So let me now
maybe one question. Do you know in advance the number of elements you would give or not?
No.
Okay.
I don't know if it makes a huge difference.
Okay.
I mean, I don't think it makes a difference because you could always like have some stupid elements that are covered by one set. So if I tell you that 1 million elements will arrive, you can have like 900,000 being, you know, covered by the same set, and then it's not interesting, right? So I think this information will not help you.
Okay.
It's different. It's probably different if you know, for example, have random arrival order. Then it's important. Then sometimes it's important to know the length of the stream. But here I don't think it. For a secretary problem, for example, it's crucial to know n. All right, so what is a difficult instance? So suppose I give you, so I have m sets, and the first element that arrives can be covered by any of these m sets. Okay, so this is the first element that arrives. How do you cover this element? You don't know anything about the future. So you don't know which sets will be useful in the future. So how would you cover this?
Equal weight on everything.
Perfect. So you kind of hedge your bets. I know nothing about the future, so let me just put an equal on everybody. So, okay, so I put 1 over m. Okay, so now I give you the constraint that all but the first set can cover this element. So what do you need to do? You need to cover this element. You have no idea which set will be useful in the future. So you just push up them uniformly, the all but the first variable. So now you will get 1 over m minus 1 there. And now you get this one. Okay, the only thing you can do is to push up this uniformly. So you get 1 over m minus 2. And you continue, and you will get that, this is 1, then 1/2, 1/3, 1/4, and so on. So if you sum up these guys, your solution would have had value, the mth harmonic number, which is just log m. Whereas the optimal solution would just be to take this Sm that covers everything. So opt is 1, your solution would be log m. It turns out that you can never do better than in a competitive rate, you can never do better than log m. So just by using this example, but not by always picking the last element, you can always make someone pay log m. So what I will do now is to give you a nice Primal-Dual algorithm for obtaining this log m. And then I will see how to adapt it using using predictions to beat this log m factor. So just make sure that to explain that even with prediction, the problem is interesting in the sense that there is this trade-off that we saw in ski rental. If we have a very good predictor, right? If we completely trust this predictor, yes, we have consistency 1, but we cannot just completely trust the predictor, right? Because if there's an adversarial prediction, he would always predict the set that is useless in the future. So then we would have paid m, which is way worse than even the online algorithm. Okay, so there is some interesting. We cannot just blindly trust the predictor. Okay, telling us which set to pick. So now let me explain the Primal-Dual method for the fractional set cover problem. So we have this primal. We wanted to cover every element by 1 unit, and we want to minimize the total sets.
Some more questions in the chat.
Do we know in advance the number of sets an element can be covered by, you mean? That number of sets an element. So in fact, you're right. So the competitive ratio will be log m, where m is the upper bound on the number of sets that can cover an element. So it's log m because if you have m sets, at most an element can be covered by at most m sets. But if you have an instance where each element is covered by at most 50 sets, then the guarantee will be log 50. You will see, I will prove this, and then it will become clear. All right, so now we have, this is the primal. I will write down the dual, which is just a covering. So I have an element, which a packing LP. So I have a variable for each element, and each set should be packed by at most 1. Okay, so this is my solution. All right, and I have non-negativity. I didn't write out. So now my algorithm is the following. Oh, sorry. So I didn't want to present it like that, so I didn't know it. So now let's present it intuitively. So suppose an element arrives. Okay, what does that mean? That means that I get a new constraint in the primal and a variable in the dual. So an element arrives. That means that I get the constraint sum of x si for all the i's such that e's in si should be bigger than 1. So if this holds already, right? Nothing to do. I already covered this element. Then nothing to do, and I'm happy. I'm happy. Okay. Otherwise, we need to do something. Otherwise, we have strictly less than 1 coverage on this element, and we need to fix it. Okay. So now for every si such that e is in si, I will increase its x variable, right? I need to increase these variables in order to cover this element. So how will I increase it? xi is equal to, so how did I do it before, right? We had an element e, Okay, it could be covered by a bunch of sets. How did I set their value, fractional value? I didn't know anything about the futures, so I put them at equal value, right? So it's 1 over the number of sets covering E. Okay, so that will make sure that I cover this element. Then you will see that the key thing to get a log guarantee is to add 2 times its previous value. Okay, so this will be my update procedure. So this here is just to make sure that I cover the element. I just uniformly spread my mass among all the sets that can cover E. And then I have this multiplicative increase of the fractional value. This will be used in order to bound the competitive ratio by log m. Okay, so this is how I cover this element. So that's my Primal-Dual algorithm, and I just put up the dual variable by 1. Okay. This is just used for analysis. You don't need to. This is just for analysis that I keep this. Okay, so this is my algorithm. Okay, so an example here. I get this element. Okay, at this time x is equal to 0, so I will set everybody to be 1/3. Then this element comes. Now I will increase S1 and S3 by 1/2, but I will also increase it by 2. So I will get 2/3. So I get 2/3 plus 1/2. And this is equal to 7/6, right? So I will set x S1 and x S3 that can cover this newly arrived element to 7/6. It's a little bit wasteful, right? I never need to set something bigger than 1. But, we are talking about log factors here. So let's just not worry about the hidden constant in this presentation. And now maybe this element comes, but I'm already covered by XS1 by 7/6, right? So I don't need to do anything here. So that's the good case. So now let me analyze this algorithm.
Again, another question in the chat, but I think you answered it already in a sense.
Don't you lose power by, are you not over? Yeah, I overcover a little bit. I overcover at most, here, right? So we will do that now. So suppose you're in this case, XS, the sum is less than 1. How much will we cover the element at most? So 2, I increase everybody by 2 times, right? So this here, 2 times the sum of 2 times, increasing everybody by factor 2 will increase the primal by at most a factor 1. Because the sum is less than 1. So if I take 2 times this, I will increase everything by 1. And then plus this is another 1. So in each iteration, my primal solution will increase by at most 2. Okay, but I will overcome a little bit cover a little bit. Okay, but at each step, the increase of the primal is at most 2. Okay, that's here. Because when I do this right here, this sum is at most 1. So I increase the primal solution x by at most 2, whereas by definition we increase the dual by 1. Okay, so this means that at the end, the value of the primal solution x is at most twice the value of the solution y. Now the problem is that the solution y is not necessarily feasible, so we don't have a 2 competitive ratio for. So that would be weird because the best is log m. So now what I will prove is that y over log m is a feasible dual solution. And then by duality, this will give us the log m competitive ratio, right? Because then I'm done. Okay, so
just to be sure that I understand. So you were just at the moment you were not. So you were increasing this yi's, ye's, but you were not worrying that it satisfies all the constraints, right?
Exactly. So if I just increase the y's and x like this, I have that the value of the x is at most twice the value of the y's. The issue is that the y's are not feasible, so I will scale them down by log factor to make them feasible. But then I have a feasible dual solution so that my solution is at most log m times the dual solution. So then I'm fine.
Yeah, perfect.
So now let's prove this. Okay, so now the observation is that every time ye is set to 1, in a constraint sum of E in SE by E1 for a set. So every time we set some YE in a constraint in the dual to 1, we double the XSI, right? We set XSI to be the doubling here. Then XSI is doubled. Okay, we double XSI every time we get a variable that it can cover. How many times can we double this variable until it becomes at least 1? Okay, we started XSI starts off with value 1 over m after one time, right? We set it to one of the sets covering. So in start xi has value at least 1 over m, and then we double it every time. But then you can double it at most log m times until it gets 1. Okay, so that's the proof. So it's a nice proof that you get the log m. Okay. So every time a YE variable is updated in a constraint, the variable xi is double in primal. We can happen at most log m times, as its starting value is at least 1 over m. And here you can see that if the starting value was like 1 over b, you would get log b times. So if every element can be covered by at most b sets, you will get log b competitive ratio. Okay. So it's not crucial if you didn't follow this, but I think it's a very nice illustration of the Primal-Dual. Okay. So now let's just return to our theme and how do we incorporate predictions. And I think this, so if you didn't follow the analysis, don't worry, you can wake up again, because now I think it's on an intuitive level. So how did the algorithm work, right? So without predictions, when an element arrived, we have said many times, and also Andre guessed, right? Hey, the way to cover this element is to increase all the sets uniformly. And this makes sense because we have no clue about the future, right? So we don't know which of these 4 sets will be valuable in the future. Okay, so we set them 1 over 4, everybody. Now, if we have a prediction about which sets is part of the optimal solution, we have an idea which should be used, right? If we would blindly trust the predictor, we would just take the sets that are part of opt according to the predictor. So this is what we're going to do. We're going to just shift the mass to increase those sets that are predicted to be part of the optimal solution more aggressively than those that are not. Okay, and this will depend on a parameter lambda. So basically, we have lambda over sets covering E instead of 1 over sets covering E. And then we have 1 minus lambda of those sets that are covered in the prediction. Okay.
And Ola, what you mean number of sets covering in the prediction is actually like with weights, right? And
so this is the sets in the predicted optimal solution that covers E. There may be many sets in the optimal solution that covers.
But I mean for the fractional problem, right? Or so meaning you would actually not have the sets.
Yeah. Okay, good. Yeah. So here it is a little bit dirty because actually our predicting is about an integral solution and we are solving the fractional. Then you can round online by losing another log factor. It turns out for the questions then that we are going to apply this framework to, the polytopes are integral. So there you don't, and you can round online. So there you don't have this weird situation. But you're right that here we have a prediction of the integral optimum that we are using to construct a fractional optimum. Okay. Very good observation. So just as an example, so in this case, if we have predicted S3 to be the opt set that covers this element, then what we would do is to set all the other sets to be lambda over 4 and XS3 to be this quantity here. So if you set lambda to be 0, that means that you're completely trusting the predictor and you only take the set S3. And if you put lambda to be 1, then you're back to the standard online algorithm. Okay, because then you just then you don't use the prediction at all and you put everybody to be 1 over 4. So this nicely interpolates between trusting and not trusting the predictor. And now I hope maybe you can see immediately, right, that the robustness is there, because now instead of setting everybody to 1/m initially, I will set everybody to be at least lambda over n initially. So this will give us an algorithm that is exactly log m over lambda robust. Okay, just because you put everybody to be lambda over m instead of 1/m in the beginning. So this is exactly the same proof as before. And you also get a very clean proof that is consistent. And why is that? Because in each iteration, you will increase the right variables a lot. A lot of mass will go towards the predicted opt if it's correct. And how much you cannot increase the predicted opt forever, right? So you just use that you are increasing the predicted opt a lot.
Just also to that I understand clearly, then these two you do not change based on the predictor. So you still double things, but then the mass
yes.
the extra mass that you add.
If you want to go down here, I've written it as a big O notation. If you want to go down to the constants, you're right that you can adapt the two to be a 1 plus delta, and you can also do the weighted version with weighted sets and so on.
But this number does not change based on the predictor. Even if the predictor tells us that the sets is not there, this you still double the weight in the same way.
Yes, exactly. Yes, exactly. So I don't, in all our applications and for ski rental, it gives the tight trade-offs. We only update the way we have this additive term and not the multiplicative term. I don't know. Yes, God knows. The multiplicative term I have less intuition for. That just is to bound its robustness by log m. Like I understand that you want to hedge your bets by uniformly adding, and then the multiplicative term is there, but it has to be there to be robust, but I don't really have a good intuition for it. Okay, so this is, a small adaptation. So now you can use predictions, and instead of having always log m, you actually get much better guarantees when you have good predictions, and you just lose a little bit. You can think of setting lambda to be a constant, right? So then you get a constant competitive when the prediction is about right, and you still have a log m competitive in robustness. So now I want to, how can you apply this general recipe? So basically, you look at your favorite question. Does it have a Primal-Dual online algorithm? And you look at how is the variables updated, and you change the rate in which you update primal variables based on the prediction. Okay, so this gives a simple analysis. Basically, you can get robustness by just using the same old analysis as before, as we did for set cover, and consistency follows by a shorting argument. And we will see that it's pretty widely applicable. So I will use it for ski rental, problem, a generalization called bond card, and TCP acknowledgement. And we also implement that for TCP acknowledgement. So let's see. So I'm not expecting you to read this, but how do you initiate it? Let's go to the book by Buchbinder and Nauer. Let's find the online algorithm for ski rental, and we see, okay, that's where they decide how to increase the primal variables, and the only change we have is if the predictions say as spying, then be more aggressive in increasing the variable corresponding to buying, and less aggressive if the predictions suggest renting. Okay, you have to think a little bit, but this gives you the robustness e to the power of lambda over e to the power of lambda minus 1, and consistency lambda e to the power of lambda e to the power of lambda minus 1. And this turns out to be recovered results by Kuma that studied this question, and this turns out to be the best possible robustness consistency trade-off. Okay, so that's that. And now if we go to a more general question, maybe a more complicated question, is this TCP acknowledgement problem. So here you have a server receives a stream of packets, and he needs to acknowledge them by sending these ACK packages. So either you can send an acknowledgement immediately when you get the packet. So you send one acknowledgement per package. So this costs you the cost of sending an acknowledgement. Or you could be a little bit lazier, so you wait, send some acknowledgement before you received a couple of packages. So instead of sending one acknowledgement per package, you can send one acknowledgement that acknowledges several packages. So now the cost would be the cost of sending a single acknowledgement plus the cost of delaying some packages. Okay, so now again, this has been studied in the online setting by doing a Primal-Dual algorithm. You can just identify where do they set the rate that they increase the primal variables, and you take into a prediction. So here our prediction is when is the next acknowledgement sent. Okay, that's what the predictor says. And this gives us the same robustness and consistency as ski rental, and that's it basically. And it's nice if you run this with some distributions. You can see that actually it works pretty well. So here, this replacement rate means that if it's 0, then the predictor gets everything correct. If it's 1, it gets nothing. They're basically unrelated to each other. Then it's just the predictor gets a random instance and the algorithm gets a random instance. And then you can see the running of the different algorithm with different lambdas. So lambda 1, that's just the online algorithm. So that doesn't care about the predictor at all. So it's a line. And then 0.4 is the one that trusts the predictor most. So this is very good if the predictor is accurate. And then you still have a bounded disaster. Let's say if the predictor is bad, you can see these lines. Yes, so that's so future directions is, we have done Primal-Dual here, Learning-Augmented for some very specific coverage linear problems. You can think of more general LPs like packing, more general convex code problems where we can take into, for example, how do you minimize speed scheduling? That's a convex function, not a linear function. And one thing that I like now is like, what if you have to pay the predictor? Then it's not so trivial. So what if, for example, in ski rental, you have to pay a cost C to get the prediction? What's the best strategy then? And like, for example, we had this paper minimizing energy and scheduling. Like, it doesn't make sense to run a predictor that uses a lot of energy if you cannot use it to save a lot of energy. So this is kind of a price in listening to calculate the prediction. And this looks like this is not so easy. So I think that's some interesting questions. And of course, you can also think about using predictions to speed up algorithms. That's also a very interesting question, I think. Okay, so that's it.
Thanks a lot, Ola, for a very interesting and very cheerful talk. So some more questions from the audience. So actually, I had one question while other people are thinking.
Yes.
Okay. Well, there is. I'll ask it later. So there is something. Is there any existing result
in
Beijing?
Yes. So there is. There is, in fact, the original paper that called is Learning-Augmented by Toros and Lukois. They did caching. And there the prediction is, I think, when this page will be requested next. And there's also been improvements on that result in terms of the trade-off. So let me see if I find here. This by Lukois and Vasilevsky and Rohatky is on competitive catching. And I think there is also now a result on weighted caching, weighted paging. So it's interesting because that is another problem where the first competitive algorithm was because of the Primal-Dual algorithm, but I'm not sure that our framework would apply there. But yes, that's a very good question. So I guess to answer your question, Banerjee, so when you say that, yes, the caching has been studied under a certain prediction model, you can imagine other prediction models. And then, so you have the problem and what kind of predictions you get. Do similar tests we guarantees online hold for online packing? So I don't know. So this is one question. So we did coverage LPs. We didn't look at much packing, but this is one of the future directions if this can be adapted. For example, add allocation is a packing LP. It's a covering that each basically you can assign each add at most once and so on. So that would be, I guess, yeah, a matching LP, packing LP.
Actually, so do these algorithms for the results that you have improved, do the algorithms differ a lot, or does it's more in the analysis part of the algorithms that they differ, if it makes sense?
Yeah, so I think the algorithms, so here, now with the Primal-Dual approach, maybe they don't differ a lot, right? In the sense that, yes, you just had to like be a little bit, you have to adapt the increase of the variables. But if you didn't have this viewpoint, then the algorithms, I think that is what makes it a little bit interesting, right? That the algorithms actually have to be clever in the sense that you cannot just blindly trust the predictor.
Yeah,
even for ski rental, so your algorithm has to somehow think about it. And so I think that is, for example, for caching, it's not that they just run the best online algorithm and then switches. No, so it's not that they just trust the predictor and then switches to the best online algorithm when the predictor is wrong a couple of steps. It's a more clever algorithm than that. So I think that is what it makes it a little bit interesting. It makes it interesting that you actually need some new algorithmic techniques.
Okay.
Any result on the lower bound on the, so no, but that's a good question. So I cannot answer there, but that's a good question. Yes. What about current? We didn't. Yes, you're right. Probably. So this has been studied in the online general covering LPs with coefficients have been studied in online algorithms. I cannot quote exactly the guarantee that they get, but I would imagine that you can do something similar. But I haven't looked exactly at that.
I also had. Sorry, go on.
And I wonder if it's not, if I remember correctly, it's also an open question what the best online algorithm is there when you have coefficients, but I'm not 100.
So what is this? I mean, for someone who doesn't know much about this, what is this charging that you mentioned about the charging arguments that you mentioned about the analysis of these algorithms? Can you like explain it in 2 words? Yeah.
Yes, of course. Actually, I can. So wait, where did I have this? So here, right? You see here that the total amount that we assign to the optimal solution is 1 minus lambda. Because if this is 1 minus lambda times the number of sets in the opt. So it's 1 minus lambda we increase opt. The way we increase the x variables of opt. How many times can we increase the x variables of opt by 1 minus lambda? Roughly opt over 1 minus lambda times.
Okay, so
after that they are bigger than 1. So that's like a 2-line argument. You increase the x variables of opt by 1 minus lambda every time. Now you can increase it at most opt over 1 minus lambda times by that amount until everybody's bigger than 1.
So it's
2 opt.
Very similar.
It's like 2 opt over 1.
Very similar to what we had with this doubling, like this log m.
Yeah, here there's not even doubling. Here it's just like we increase the x variables by 1 minus lambda every time.
Yeah.
So
that's it. Yeah. Okay. Great. So any more questions? Oh, it was, I think, it was a lot of questions, which is very nice.
Yeah, no, it's great. I agree. Very nice. Thanks a lot.
Yeah, thanks a lot, Ola. And so we'll have one more talk by Josef Balak in an hour. And thanks a lot for your wonderful talk, and hope to host you in Moscow sometime soon.
I will look forward to it. Thanks a lot.
Okay.
Bye-bye.
Bye-bye. Bye-bye.